Hello and welcome back to PC Retro Programmer. In this video I'm going to take you through a very simple assembly language program which is just going to print the words hello world on the screen and then exit immediately to DOS. It's about the most simple thing you can do other than just quitting immediately, and it's a TASM example. So if you have the Turbo Assembler installed, then you'll find it in the TASM directory, and it's called hello.asm. So you can see it's fairly short and it has the .asm extension, of course. So let's open this in an editor and see how it actually works. So I'm just using the DOS editor here, and you can see that it's relatively short, but still quite a lot of code for something so simple. But rest assured, a majority of this is just stuff that has to be there for pretty much any assembly language program that's going to be assembled to .exe file. Now over on the right here we have some comments which have been added by whoever wrote this program just to explain the individual steps. So everything that is after the semicolon here is just ignored by the assembler and doesn't contribute at all to the final executable. Now let's take a look at this program to see how it works. First you'll notice that there's only assembly language instructions from line 7 to line 13 here, and these are the only lines that actually get assembled into machine code to be run on the CPU. Everything else here is basically boilerplate code to tell the assembler how to do its job, and ultimately to tell DOS how to load the executable into memory when you run it. There's one other line here which contains some data, and that's our text string that we're going to display on the screen. So let me talk about these assembler directives at the top of the file here. The first one is DOSSEG, which tells the assembler to use the DOS convention for segment ordering. Well, first of all, what is a segment? In the CPU you have 16-bit registers, and if you try and get addresses into 16 bits, you'd be limited to 64 kilobytes of memory. Now, 8-bit machines have this restriction, but the Intel 8086 and 8088 can actually address up to a megabyte of memory using a trick. So what they do is they have 4 internal registers called segment registers, which store the start addresses of 4 64K blocks of memory. So this enables them to deal with 4 64K blocks at once, which can essentially be anywhere in memory. The only restriction is that the start addresses have to be divisible by 16, because what they do is they take those start addresses and they divide by 16 and put those values in the segment registers. Once you've divided by 16, the values will actually fit into a 16-bit register. So in the 8086 and 8088 you have the CS register, which is for the code segment, and that will contain all our code. You can see that here. You'll have the DS register, which contains the start address of the data segment, which will contain all our data. There's SS, which is the start of the stack segment, and I'll talk about the stack a little bit later. And then there's a fourth segment, the extra segment, and there's a register, the ES register for that. So for the DOSSEG directive, what it's saying is that we want our segments to be in the order that a higher level language would order them in memory. Now I'm not actually sure that this DOSSEG directive does anything at all when you're using just .model, .stack, .data, and .code. But there are other more complicated ways of specifying segments, and then you may need this. Even the manual says you don't really need to know how this works. The only things you need to know is that if you're writing a standalone assembly language program, you should put this in, and you only need it in one file. So the next directive here is the memory model. Now, the simplest kind of program would have all the data and all the code fitting in just a 64K block. That would be much more like programming an 8-bit machine where you just restrict it to 64K. And so that's a tiny memory model. This particular program uses a small memory model where you actually have separate data and code segments, but they're still restricted to 64K. And then there are other memory models for where you might have more than 64K of data, or more than 64K of code, or more than 64K of both. And of course in that case you have to do some work to keep changing the DS and CS registers when you move about to do different 64K blocks, because the processor is still limited to 64K even if you've got more data or more code than that. There's also another memory model which is just useful for higher level language programming, and I won't go into any of these. It's just enough to know that for fairly straightforward assembly language programs, this small model is going to be fine. It's unlikely that we're going to get more than 64K of data or code at this point. So the three directives that define our segments here are the stack, data and code directives, and you shouldn't think of these as actually being 64 kilobytes. They're not taking up that much memory. In fact, they'll be made as small as they possibly can. Those segments that the CPU can address, they are 64 kilobytes each, but there's no restrictions on the start addresses other than they're divisible by 16. So it would just pick start addresses which are as close together as they possibly can be and still fit everything in. And so they'll end up overlapping in our case. In this particular case, we've got a stack segment of just 256 bytes. So 256 is 100 in hexadecimal, which is why it's written this way. And of course our data segment here just contains a short string, so only a handful of bytes. And our code segment isn't very long either. These assembly language instructions really boil down to just a few bytes each at most. So we're going to have very, very short segments here. There'll be multiples of 16 in length, of course, but they certainly won't be 64 kilobytes each. The CPU can still read to the end of the 64K from the start address in each case, but this is probably not something that we actually need to use in our program here. So now let's talk about the program itself and also the data string. The first thing that our program does is to load the DS register, the data segment register, with the start address of the data segment. Now the reason we have to do this is that DOS only loads the SS register with the start address of the stack segment and the CS register with the start address of the code segment for us. It doesn't do the DS register, that's our job. But even so, we don't know what this start address is going to be until the program is loaded by DOS. And so we need to put a special symbol in here to tell the assembler, hey, DOS needs to fill this value in. And so we use @data for the start address of the data segment. Now unfortunately we can't put this address, it's a 16-bit value of course, directly into the data segment register, and the reason for that is that these segment registers are very primitive. They don't have many assembly language instructions associated with them, and they don't have a lot of functionality. In fact, you can pretty much just move data in and out of them via general purpose registers, and that's exactly what's happening here. So DOS will fill this value in. It'll be the actual address divided by 16 of course, and we move that into the general purpose register AX. The destination is always on the left, by the way, and then from the AX register we can move it into the data segment register. Now we could have used any general purpose register here. There are lots of these. There's AX, BX, CX and DX. There's SI and DI, and there's SP and BP. Now you probably wouldn't use the latter two because these are probably in use for stack related stuff, but in theory you can use any of the general purpose registers here, and AX is not in use for anything here, so that's the one that was chosen. Now the next three lines of the program are for printing the string on the screen, and this uses the DOS print string function. Now this is not what a function call would normally look like. If we'd written this function ourselves, this would look quite different. We'd use the call instruction. But to actually call a DOS function, we have to do it via the DOS interrupt. So there are lots of interrupts. The BIOS has a whole pile of these, and there's a few others as well. But DOS uses the interrupt number 21 hexadecimal. Now to tell it which function we want to call, we can look up a table of DOS functions for the DOS interrupt, and there's a whole pile of function numbers. And the print string function that we want has function number 9. And DOS will expect us to place that function number in the AH register. Now the AH register is actually the upper byte of the AX register. So the registers AX, BX, CX and DX are each divided into a high byte and a low byte. So we have AH, AL, BH and BL, CH, CL, DH and DL, each a byte. The other general purpose registers aren't divided into bytes that way. So anyway, DOS expects the function number in AH, and the other thing that it's going to need is the string itself. Now we certainly can't get the string in a 16-bit register. This is numerous bytes, so it certainly won't fit into 16 bits. But instead we put the string in memory, in this case in the data segment, which is really what the data segment is for, and then we just put the address of that string into the DX register. Now what DOS expects here is for us to put the offset within the data segment of the string into DX. Now I can tell you that offset is going to be 0 in this case because it's the very first thing in the data segment, but that need not be the case. We could have other strings and other pieces of data that we'd defined, and it would just be a pain in the neck to have to compute the offset to get a number that we could put here. And so this offset directive computes that for us. We just have to give all our pieces of data a name, and then we can refer to them by name, and then offset will compute that offset within the data segment on our behalf. Now the final thing that happens here is we just actually call the DOS interrupt. So this is a routine that's somewhere in memory that DOS has provided for us, and the CPU knows how to jump off to that. There's a table of interrupt addresses called interrupt vectors right at the very start of memory, so it jumps to the one for the DOS interrupt, but then it has to return back to our program once the function has finished running, and somehow it has to know where to jump back to. So the way that it does that is using the stack. So whenever you call a function or an interrupt in assembly language, the CPU will record the address that it needs to return back to automatically in a piece of memory called the stack. And so that's what we defined up here. We set aside 256 bytes for the CPU to record these return addresses in. Now we're not going to use very much stack here. We'll put one address on the stack here, but when this function returns, it'll be taken back off the stack again, and the stack will be empty. And similarly, we put one address on the stack here. But of course the functions and interrupts can call one another. In fact, the DOS interrupt might actually call other functions. So you can end up with a big long chain of functions that all call one another. And so you can end up with quite a few different addresses put on the stack. And then as these functions return one after the other, they'll be taken back off the stack, and eventually when we get back to here, there'll be nothing on the stack again. So you need a little bit of space on the stack, and this is a reasonable value for a smallish program like this. But if we had lots of functions that were going to call each other in very deep chains, then you might need a bit more stack space. Finally, we call the DOS terminate program function here, which is function number 4C, and that again has to go into the AH register, and we call the interrupt, and the same thing will happen here, except that this particular interrupt call won't return, because the purpose of the terminate program function is to return control to DOS. So it would now be back at the DOS command prompt, and our program doesn't get control back. So it doesn't ever have to return from this particular interrupt, but that's a special case, of course. In all the other cases it's going to do that. Now the other thing that the stack is used for is for function parameters. Now we don't have any ordinary functions in this program, but if we did, we would pass the arguments to the functions on the stack. So that's another reason why we might need some stack space. But there's a little bit of space here for our program to grow. The final thing here is the end statement, which just tells the assembler where the end of the file is, and if you leave that out, it'll complain. So you have to put this in every file. Now, the final thing to discuss is the string itself, and as I said, we give it a name just so we can refer to it. This hello message doesn't actually end up in our final executable, it's just for convenience, so we can talk about this particular piece of data. And we use the define byte directive here, db, and normally what this would expect is the bytes separated by commas, pretty similar to how we have it here. So a byte is just a value from 0 to 255. In this case these are decimal values, but you could use hexadecimal as well. That'd be a value from 00 to FF in hexadecimal. And so you just have these separated by commas, but that would be a bit laborious in this case, because the values that we want for our bytes here are the ASCII codes for the characters in our string. Now you can look these up in a table for ASCII codes. You could look up capital H and put its value here followed by a comma, then look up little e and put its ASCII code followed by a comma, and so on. But the assembler saves us all that hassle. Basically, if we put our string that we want inside these single quote characters, it will just replace that with all of the appropriate ASCII values. And to do a new line, both DOS and Windows actually use this special combination of ASCII characters. There's a carriage return and a line feed here. So I think carriage return is supposed to go back to the start of the current line, and line feed is supposed to go to the next line. But anyway, the DOS and Windows use this particular combination of carriage return line feed to signify the end of a line when you're printing stuff on the screen. So you could have multiple lines printed by one string. You just have to terminate each of the lines with this CRLF combination. Now, the final thing that we need is something to tell DOS that we've reached the end of the string. Otherwise it will just keep printing whatever's in memory and you just end up with garbage in the screen. And so DOS uses the $ character for this print string function to tell it that we've reached the end of the string. Now the $ isn't printed, it's just a special code for DOS. And that means you can't use the $ in your string, otherwise it would just end early and you wouldn't see the whole string. So that's basically everything. So now we just need to exit from this and assemble this program, and then we can try it out. Now, assembling our program is a pretty straightforward process. The first step is to call the assembler, which is TASM, of course, and it's enough to just give hello, but you can also put the extension if you want. It will assume .asm, so it's really not actually needed. So if I run that, it'll run relatively quickly because it's a very short program, and it tells me there are no error messages, no warnings, and now it has created an object file corresponding to that assembly file. So for each assembly language file in your program, you'll run the assembler on it and you'll end up with an object file. So this has now got some machine code in it, and it's also got some information for the linker about how the files should be linked together. So in this particular case there is only one object file, but if you had multiple object files, the linker would put those all together into a single executable file. So to link, we just call tlink, and again we just do hello. It will assume .obj, And if we had other object files that we were linking together to make our executable, we'd put those separated by spaces on the line. So let's run this, and we'll see that it runs extremely fast, and this has created our final hello.exe. So you can see that that's quite a large file. 543 bytes is quite a bit. There's only a very small number of bytes, a handful of bytes actually, for our actual assembly language program. The rest of this is basically a header, and that header tells DOS how to load the program into memory and various other information like that. So I can now run this program. It's just a normal DOS executable, and of course it does exactly what we expect. It prints hello world on the screen and then immediately exits back to DOS. So this is a very simple example to start us off. We'll deal with some more complicated ones as we go, but it is useful to be able to print stuff on the screen. Obviously anything that you want to display to the user, or even if you're debugging your program and you just want to print out the value of some variable at a particular point while the program is running, you can use a print for that. And so this is a useful technique nonetheless, but it is just an introduction to get us started.